Sounds like my house, Tommy. Although usually it's with bacon. We can't cook bacon in our house without the fire alarm going off. All right, good morning, everybody. I hope you guys are doing well today. That is a picky fire alarm. All right, couple of announcements. I don't have it on the board, but I know that you guys are well aware of this already. The quarter 1 deadline is this week Sunday. It is daylight savings times as well, so you gain an extra hour. We fall back um, Sunday morning, really early Sunday morning. Um, but just make sure you have everything up to and including 3.04 turned in. 3.04 was the lesson that we covered in Tuesday's class. So if you have that turned in, you should be good to go. Obviously, we are looking at 3.05 today, but 3.05 extends into next week. And you don't have to have that turned in before the quarter deadline, which is Sunday. Um, the other thing I want to make note of is that Monday is technically a half day for you guys, which is kind of weird in the virtual world. But what I did is I treated it like a full day off of school. So I did not assign anything for on the calendar for that day. So if you're caught up with everything, maybe use it to work on your electives or you get a day off. Um, Really, that's the only announcements that I have. Did you guys have any questions with anything? You know what? If I knew how to answer that, I would definitely let you know because I probably would be sleeping and teaching math at the same time. Right? It's a pack. So whoever figures it out first has to let the other one know. Sounds like a good deal to me. Right? Right when I'm about to retire, you'll figure it out. All right. So today we are continuing on with our logarithmic and exponential functions. Um, and I said exponential in there because we are tying the two together today in order to solve our equations with them. We have been working a little bit on how to use some of our properties to solve exponential and logarithmic equations, but today that's going to come kind of full circle and we're really going to look at different strategies on how we can solve these equations. Okay, so the first strategy we're going to talk about is getting the bases the same. So we notice there's lots of different logarithmic and exponential functions we can be presented with throughout this unit. So in example 1 here, this is just one um, example that we are going to see. Notice that the exponent has our variable in it. If that's the case, you always want to try and isolate the base first. So that's always going to be kind of your first technique no matter what you're looking at is let's try to isolate whatever that base is. So can I add or subtract things? Can I multiply or divide things to try and get that base by itself? Once the base is by itself, then we can start using some of these properties to get that exponent down from up there and solve for that. All right, so looking at example 1, what would I need to do here to start off this problem? So if I have 20 times 1/2 to the x divided by 3 power equals 5. Yeah, I had just got done saying isolate that base, which means get rid of the 20 that's out in front by dividing by it. Okay, so that's going to give us a 1/2 x divided by 3 equals 5 over 20, and I'm hoping that everybody is comfortable with me just reducing that to a 1/4 right away. So is everybody good with how we got the 1/4 there? So 5 over 20 is the same as 1 over 4. Great. Then, once your base is isolated, you have a couple different strategies you can do. From here, we would try, one strategy is to try to get the bases to be the same. Because the first property we have states if the bases are the same, then they drop out and the exponents will equal each other. I don't have any logs actually present in this setup, but the same thing holds true if you have logs with the same base. So if you have log of the same base on both sides of the equal sign, those also drop off and you're left with just the u equals v part there. Well, I don't have the same base, but I think we can rewrite the 1/4 so that it is a base of 1/2. Yeah, so Tommy says, well, let's go ahead and rewrite the 1/4. So it is a 1/2. And if we write that as a 1/2, you've got to make that to the 2 power. Great. Questions with that step, because that's probably the most crucial step of this whole thing right here, is noticing we can change that base of 1/4 to 1/2 and raise it to the 2nd power. Okay, so now that the bases are the same, they drop out. We can use that property up above, and we set the exponents equal to each other. So x divided by 3 equals 2. And now this is a very simple algebraic equation here left for us to solve. What is x going to equal? 6. Yeah, and you always want to check your work. Substitute it back into the original equation and run through that real quick. Make sure you do get 5 equals 5. So we always want to check that work. Yep. And I did things a little bit in my head as I typed that into the calculator, but I did get 5 equals 5. Good. So it works out. Yay! Sometimes they don't always work out, so we always want to check to make sure. Okay, so that is one strategy. Any questions with that first strategy of getting the bases the same so that they drop off and you're left with just the exponents equal to each other? Okay, the second strategy is panicking. No, I'm just kidding. It's not. When we see a problem like number 2 here, our heart does rate, like my heart beats a little bit faster when I see something like that, because I'm like, oh man, I don't know. I'm not the greatest with base E here, but I'm going to use my techniques that I've gained so far. Well, we haven't gained too many techniques, but what would you try to do to solve this problem? What might be your first step? Yeah, multiplying by 2. So when we multiply by 2, that gets rid of the fraction on the left-hand side. But it doesn't really make our problem any easier. So, what might we try at this point? So I can't get the same base. That's kind of thrown out the window. Kind of hit like a dead end. The e's are already separated with the minus sign, so I'm not quite sure if we can separate them anymore. You mean like add one? I'm not sure if that will do much for us, because I can't see where we would go after that. That was a good thought, though. Could we use it in natural log? Maybe. I keep every way I think about it though, I kind of hit a dead end almost. I can't really think of how we could simplify that to move any further. So if you get really stuck at a problem like this and you can't go any further, what the second strategy I want you to try is graphing. So technically there are two equations here. You have one on each side of the equal sign. So here's one equation, y equals this. And then the other equation is y equals the 10, which is on the other side. So if you get stuck and can't figure out how to move further algebraically, graph it. Now we might need GeoGebra to help us graph this, to be honest. I could try to bring it up in this graphing calculator, but I'm not sure if it'll show nicely or accurately enough. I'll give it a go though. We'll see. If you guys want to go ahead and use your graphing calculator or GeoGebra to graph this, oopsie, it might be better because they have more accurate tools than this calculator does here. That should be a horizontal line. Let's see if it graphed it. There it is. We're looking for where the two graphs intersect because that's where they're equal, right? So I'm really interested in what's going on at this point right up here. What is that number? 2.3110. Good. So we're looking for the x equals, right? So if it's x equals, that is your 2.31 value. So when in doubt, another strategy you can do is graph and see where the two lines are going to intersect each other. It's a strategy we actually haven't used for a while because we have been able to do a lot with our algebra skills. But this is another strategy that we can use to help us solve, especially with some of these, I don't want to call it ugly looking, but it is kind of ugly looking exponential function. Sorry, any questions? My voice cracked a little there before I turned the mic on. Any questions with how we did that graphing one? I'd obviously like us to try to solve these algebraically first if we can. Okay, with that being said, now I do have a log that's thrown in. So now we're not looking at the exponential, but now we're looking at the logarithmic equations. So we're going to talk about strategies to solve these logarithmic equations. So the first strategy I want you to use is, well, first I want you to see how many logs do you have. Do you have a log on just one side of the equation, or do you have a log on both sides? If you have a log on both sides, then we're going to use that property we saw at the very beginning where we want to get the logs the same, they drop out, and we're dealing with what's left over. If you have just one log on one side, like we have in example 3 here, you have to change this to exponential. So we're going to go ahead and use that formula to help us switch this to exponential equation. Once it's in exponential form, you should be able to solve for the x in there. All right, so remember, to switch to exponential form, you start with your base. So the base, remember, if none is written, is 10 because that's your common base. The next is figuring out what the exponent should be. What should the exponent be if I'm switching to exponential form? It's going to be the 2. The exponent is always what's on the other side of the equal sign here. That means we're going to have that equal an x squared. All right, this problem just became, hopefully, a lot easier for you to solve. So changing from logarithmic to exponential form has allowed you to solve for x. What values work here? 10. Is there anything else besides just positive 10? And when I say positive 10, that really kind of sheds light on what else it could be, right? Negative 10 should also work because when you square a negative, that's going to turn into a positive. Yep, so negative and positive 10 should work here. Now, if only they were all like that, right? Unfortunately, they're not going to be all that easy to solve once we switch to exponential. Okay, speaking of not so easy, let's take a look at example 4. There's technically 2 different routes you can go about solving this one. So first of all, let's talk about it algebraically because it can get a little bit lengthy. All right, what might we try to do to solve this logarithmic equation? I see lots of natural logs. So what can we try to do? Any ideas for me? Ooh, I would love if we could cancel some of them. Move the 2 up. We can't take out, I like the idea of moving the 2 up over here as your power rule. I like it. That's not the only rule we want to do though. We can't cancel the natural logs until you have just one of them on each side. So I like the idea of being able to cancel eventually, but we need to condense the left-hand side. Right, so we have to use those properties of natural logs to condense that. So if you have if you have adding in there, you want to multiply those 2 things. Good. Now that you're down to just one natural log on each side, they drop out. All right, here comes the fun part. Let's actually multiply this out together. 3x squared minus 3x minus 2x is a minus 5x in the middle. Plus 2. Where do I go from here? Let's drag up those algebra skills from the past. Subtract the x squared from both sides. Here comes the fun part. What's left? Factoring. And it is the ugliest factoring problem that we can run into because we have a 2 in front of the x squared with no GCF that we can pull out. So remember, we can turn this into factor by grouping. So you can take the first and the last terms here, multiply those together, and then look for factors that add up to that middle number. What are factors of positive 4 that add up to negative 5? Negative 1 and negative 4. So that means I'm going to rewrite the polynomial, and instead of having the negative 5x in the middle, I have a negative 1x and a negative 4x. We're going to group 2 of them together at a time and take out the GCFs. What's the GCF of the first parentheses? An x. Okay, so as I'm writing what's left over here, what is the GCF of the second parentheses? Gosh, your factoring skills are on par. Woohoo! And we want the same thing to be left over, right? If it wasn't, then factoring doesn't work here, or we made a mistake. But we want the same thing to be left over. All right, then what can I do to solve for x? Set each of them equal to 0 and work backwards. So that's going to be what, a positive 2 and a positive 1/2. All right, let's divide and conquer here. We want to make sure that this actually works out in the problem. So let's go ahead. Somebody take the 2 and somebody take the 1/2. Let's substitute in and see if we get a true statement using those. Okay, I took the 2. The 2 worked out okay. So now we're waiting on the 1/2. Okay, 1/2 we run into an error, right? So I tried doing just the left-hand side and we ran into an error. Anybody know why we ran into an error? Where does the problem actually occur on that left-hand side using 1/2? So 1/2 gets thrown out. Logarithms cannot be negative. So right here, this is what's giving us the error. 1/2 minus 1 is a negative 1/2. And we have the domain for natural logs have to be 0 or higher, right? Only 0 or positive work. Because that gave a negative output, we can't do it. So 1/2 is not actually going to be our solution. Only 2 works, which is why I want you guys to check your answers all the time, because you can get an extraneous solution like that popping up with your natural logs or your logs. All right, if you didn't know how to go about this algebraically, what's the other method you could have tried here? What's another strategy? You could have tried graphing. Yep. So you could have set y equals to this mess over here, y equals to this, and then seen where they intersected at. They should have intersected at x equaling 2. So again, 2 different strategies you can go about solving there. I really like the algebraic approaches though. Okay, from here on out, we're simply just practicing with all the different strategies on solving these exponential and logarithmic functions. All right, so let's take a look at the first one here. What ideas or tips do you have for me to try to solve for x in this problem? Divide by 32, and the more we practice and the more we do of these, the easier they become, right? Just like with anything. The more you do, the better you become at it. So let's go ahead and divide by 32 to start off with. That's going to leave us with a 1/4 to the x minus 3. And what is that, a 1 over 16 on this side if I reduce properly? Okay, so now that I reduced that fraction of 2 over 32 and made that a 1 over 16, what can I do from here? What's the strategy we're looking for? Try to get the same base. If we can get the same base, then those drop off and you're left with an exponent, right? So we want to try to change that 1 over 16 to match the 1 over 4. And it does. They're not going to give us anything extremely complicated with trying to match a base. So that's the good news. Most of those are going to be easy to kind of pick out there. Yep. So again, the bases drop off. You're left with x divided by 3 equals 2. which is x equals 6. Try it out though. Does it work? Is it okay for the problem? I don't see it actually being an issue with an exponent there because negatives are going to be okay with the exponents. It's just the logarithmic ones we may have to double check more closely or keep an eye on. But I think that one's going to turn out to be okay. Okay, Tommy verified for that. Verified that for us, and it does work out. Awesome. All right, how about the second problem there? Strategies, ideas on how we can solve for x. Start by dividing by 3. All right, so I'm going to divide by 3. Let's see, 96 divided by 3, 32. Does that sound right? Thank you. Now what? There's a couple different things we can actually do here. What's one idea that's rolling through your head right now? What's one thing we're trying that you might be thinking of to proceed? You can graph it. You definitely could graph it. Yep. So even if you get stuck at this point, you could graph it. What's another strategy? What else could we try to do? You can find the same base. You're right. If I want to try to find the same base, 4 and 32, it doesn't work with 4, right? There's no way we can write 32 with the base of 4. However, can we break down both bases a little bit more? So I'm thinking I can break down 4 into 2 squared. Can I do the same thing with 32? So if I break down the 4 so that it's a 2 squared, can I break down 32 so that that is 2 to some power? I can. Okay, 2 to what power is 32? 2 to the 5th. All right, so what do I want to do over here real quick though with these exponents? So if there's just a parenthesis that separates them, you multiply them together. Multiplying them together is going to give me just 2 to the x power, right? So technically these are going to cancel out. What else cancels out from my problem now? The bases. So the bases also cancel and you're left with x equaling 5. So once we could actually determine how to rewrite those bases so they were the same, it went really quick for us. But it took us a while to realize that we can break down both bases still to get them to equal the same thing. All right, and you can go ahead, test that out. It should work okay for the problem there without any issues. All right, what about problem 3? Ideas for problem 3 for me. All right, I like it. Let's divide by 3 to start things off. See where we end up at. 15 divided by 3 is a 5. Ooh, we lucked out quite nicely. What happens at this point? The bases cancel out. When the bases cancel out, what am I left with then? Obviously, I have the negative x over 4, but what am I left with on the other side? Careful. A 1. Yeah, remember, and if you have just a constant, the exponent is a 1 there. So not a 0, but a 1. Yep. Now you can actually proceed forward. What is x going to equal here? So 2 quick steps, technically 1 if you move the negative sign. Yep, that's going to be a negative 4. Testing that out, a negative 4 is a positive 4. 4 divided by 4 is 1. 5 to the first power is 5. 3 times 5 is 15. So it works out okay. All right, we're getting better at this. What about the next one? We're dealing with a log. So now we got to think of some of the logarithmic strategies. Change to exponential form. Love it. So you only got one log here. Try to change to exponential. Perfect, Isaias. And Rebecca had that too. Good. So how does that change to exponential form? How can I write that as an exponential? Two to the fifth power equals x. And now that is simply just a simplification problem. 2 to the fifth power, didn't we just get done saying that was 32, right? Up in the other problem. If I wanted to verify that this works out, what would I need to do to verify that? You have to use the change of base formula. Very good, because notice you don't have base 10, so you need to use the change of base formula. Log of 32 divided by log of 2, does that actually give you an output of 5? And punch it in real fast, does it work? It does. Awesome. All right, last one on this page, strategies on how I can solve for x in this one. Change to exponential yet again. Yep. So I'm going to go ahead, pick a color we haven't used yet. I'll do orangish, I guess. How is this going to be written in exponential form? I know you guys are probably already working on typing that up. Yep, 4 to the first power, which is just 4, equals your 1 minus x. All right, do your magic here. What is x going to equal? -3. All right, it's a negative. I get a little bit iffy with negatives and logarithms. Check it out, substitute it back in. Is it going to work out okay? It does, yep, because that's actually going to turn into a 4 inside the parentheses. Log base 4 of 4. We know we have that property is going to equal 1. Very good. So good use of your strategies here with these 5 problems. Any questions with those before we look at a few more? All right, let's take a look at a few more. How about this one? What might you do for this one? This is a strategy we haven't necessarily brought up today. You can definitely graph it. We've used this strategy in the past, but I haven't talked about it today. If you're given an exponential function like the one we have here, and you obviously can't figure out the same base, you can definitely graph it to see. Another option is to take the natural log or the log of both sides. So I know that we've talked about that in the past, but we haven't seen it used today yet. So this is an example where we can go ahead, take the log of both sides, and when I do that, I can bring the x down out front using that power rule. Log of 0.98 is just a constant. So if you divide by that on both sides, you will get your x value. So algebraically here, what do we get for x? So if I'm using this method here, what is that going to equal? A negative 23.26. Ooh. If you graphed it, you should get the same thing. Okay, so yet another strategy introduced to us. Technically not a new strategy, just one we haven't used today yet, but it still works nonetheless. All right, question 2. What would you try to do to solve in question 2? Yep, try to isolate the base still. That's always your first goal, is to isolate the base no matter what. So we want to divide both sides by 80. What do I get when I divide by 80? A 3. Thank you. All right, then what? Now that we've seen the first one worked out, hopefully a way to proceed kind of pops into your head for this one. Yeah, because you're dealing with the base e, you're going to want to take the natural log of both sides. Taking the natural log of both sides allows you to bring down that 0.045x. Natural log of e, natural log of 3. What happens with the natural log of e? It cancels, right? They undo each other. They're inverses of each other. So technically you're just left with 0.045x equals the natural log of 3. And there's just one last step to get x by itself from this point. What is x going to equal? A 24.41. All right, any questions with that one? Now that we've kind of seen a couple of these worked out, the rest of them are really going to kind of hopefully pop for us on what strategies to use to solve. Okay, in question 3, what's the strategy we can use here? So what would you do? Start by trying to isolate the base. So the first step is subtracting 7. Then what would you do? Divide by negative 3. Okay, that is going to be a positive 5/3 once we divide by the negative 3. Great. Now what? Now you can take the natural log. I know that the natural log of e is going to cancel out, right? And I'm kind of writing over, sorry about that, writing over the pink answer from above. We have to use a calculator to figure this out. What is that going to be though once I use the calculator? A negative 0.511-ish. Okay, any questions with that one? You guys are flying through these. All right, how about the last one? What are some ideas for me on the last one? You still want to try to isolate that log first. So start by subtracting 3. Then what? You have to divide by the negative 1. Good. Notice you can't leave that log negative. All right, now what? Now you change to exponential form. You only got log on one side. Change to exponential. Your base, write the exponent, what it equals. I'm going to come over here to keep working. What is 10 to the negative 2 power? One over 100, so 0.01. Looks like I'm going to subtract 2 from both sides to get that x by itself. And what do we end up with for x? A negative 1.99. Test it into the problem, see if it works out okay. It should, because when I'm looking at the parentheses and log there, it's going to be a positive value in there. So we should be okay, but just double check it just in case. So Tommy says, yep, it does work out okay. And Rebecca says, we are good. Awesome. All right, any questions with what we've done so far today? I've just got one last set of problems here for us to try to work through. And it says, solve each equation by the method of your choice. All right, so these are, I think, a little bit more complicated, but once we see kind of the first one done, the rest just kind of fall into line. So what would you try to do on that first problem? Natural log of x squared equals 4. You're going to turn it into an exponential form. Perfect. How would I write that in exponential form? What's my base? Not 10. Careful. It would have been 10 if it was a log. Yeah, but now you're working with natural log, so the base is e. E to the fourth, though, is still just a constant, so you can get a value here. How are we going to get this by itself? So what do I need to do? Because it's not an x equals yet. It's an x squared. So what do I technically have to do to both sides still? You got to take the square root, not square it. Take the square root. Okay, when you do that, don't forget you technically want to put a plus or minus sign in there. I'm going to just leave it like that. You can get a numerical value. If you have a calculator, what is the numerical value of the square root of e to the fourth power? About a 7.389. And Isaiah seconds that. Okay. You can leave it as the exact answer as the square root of e to the fourth, or the decimal is fine. Exact is always better, but the decimal here is acceptable as well. All right, knowing that, how do we proceed with the second question? Yeah, you can change to exponential. So e to the 12th equals x to the 6th, right? Then what? Take the 6th root. Yes, take the 6th root, which is a little strange, but it actually works out quite nicely. I will get an x here, and I'm taking the 6th root of e to the 12. Can I take the 6th root and make that a fractional exponent? What is the 6th root as a fractional exponent? A 1/6. Yep. So technically I can write e to the 12th times the 1/6 power there, right? And 12 times 1/6 is just a 2. So this actually does simplify quite nicely down to just an e squared. This is the exact answer. E squared is a constant, so if you have your calculator, you can get a decimal representation of that. What is the decimal value for the e squared? Oh, I guess it would be the same thing, wouldn't it? Because that's the square root of e to the fourth. Looky there. Same thing as last time. All right. I know, right? It makes you stop and wonder, like, uh-oh, what did I do wrong? But no, it's good. We didn't do anything wrong. The last one. Okay. Actually, we probably should do plus or minuses for these. Yes. Anytime we're taking the root of anything, we probably should put a plus or minus out in front of it. Yep. Especially with your even. So we want to do that with the even roots because that's when you square it, it turns back to a positive, right? The odds, not so much, but the evens, definitely. Okay. How about the last one? The last one makes me panic. My heart starts to beat a little bit faster with the last one. But at least I can identify what the first step is going to be. Multiplying by 2. I want to get rid of that fraction. All right. Then from here, it looks very similar to a previous one we did. What is the strategic method that you want to go with to solve from here? Graphing, for sure. Algebraic, I don't know. It might be quite messy that way, so let's graph it. Change that one to the 6, and instead of a base E, I think it's just a base 2, right? That's the only thing that changes. Oh, and the plus sign. So 2 to the x plus 2 to the negative x. Okay, I got to zoom out. Oh, we got a parabola going here. Awesome. So we actually have 2 values. What are those approximate values? Plus and minus 2.54. Fantastic. All right, nice job, guys. Any questions with the strategies or methods we use to solve these logarithmic and exponential functions? All right, that's all I got for you then today. So I will let you go. I do have office hours. I think I have a couple slots open for today still, and then maybe one for tomorrow. They're filling up quick. But I actually think you guys will be just fine. Remember 3.04, everything up to and including 3.04 has to be turned in by that Sunday deadline for this week. All right. Good luck with everything, not only in this class, but all your others. And I will see you guys again Tuesday. Bye, everyone.